Hello, this is Monique Morton, Senior Content Director for Mathematics and Computer Science with Advanced Kentucky, and this is another mixed optimization problem for AP Calculus. Let's read the problem. A sheet of metal 12 feet by 15 feet will be made into a box by cutting equal sized squares from each corner and folding up the four edges. What will be the dimensions of the box with the largest volume? So in this case, I'm going to draw a diagram. I've got a rectangular sheet of metal that's 12 feet by 15 feet in diameter. Well, the lengths are 12 feet by 15 feet. And what we're going to do is we're going to cut out little squares in each corner using little dash lines to show you where the squares are going to be. So that when we cut out the squares, cutting these out, we're going to fold up the sides and make a box. The box is going to look sort of like this. Oh, math teacher, not an artist, but you get the drift. Okay. So, I don't have any variables in there, but I don't know the dimensions of the squares. So let's just label the sides of the square x, and since they're squares, all of the sides would be x. And that's the only dimension I don't know for sure. I don't know how big to make the squares. So I'm thinking that the volume that we're looking for is going to be dependent on the square. I'm looking for a largest volume, right? And my box, which will have an open top, define the volume of it. Volume would equal length times width times height. So we're going to need to find expressions for the length, the width, and the height. So we're going to fold along these lines, right? I'm just going to extend them out a little bit. So the height of the box is actually going to be the length of one corner of the square, right? If I call this the height. So the height is going to be equal to x. And let's call this the length and this the width. Doesn't matter what we call which. We're just going to write some stuff down. Okay? So let's say that this side here corresponds with the length. Well, it's 12 feet from end to end before you cut the squares out. But the actual length would be the length of this segment here after I cut the squares out. So I'm going to cut off 1x, 2 x's to get the new length. So the length is going to be 12 minus 2x. Likewise, on this 15-foot side, it's 15 feet from edge to edge before I cut out the squares. But after I cut out the squares, I'm going to cut off 8 feet this way, 8 feet that way. So the width is going to be 15 minus 2x. And so my volume expression as a function of x is going to be 12 minus 2x times 15 minus 2x times x. That's my volume expression. Okay, so now that we have our volume expression, I'm going to go ahead and write this. I'm not going to show you the steps in multiplying this out. I'm just going to tell you what it is. This is 4x cubed minus 54x squared plus 180x. Here's my volume expression. And the reason I took the time to multiply it out and did it over on the side is because I need to take the derivative in order to be able to maximize the volume. So let's talk about domain real quick. So since this is 12 feet wide, this is smaller of the two, so I'm going to start with this side. Okay. I know that x can only go like halfway through. It can't go past halfway because I can't cut out two squares that way. And the farthest I could go then would be 6. So this tells me that my domain for x has to be limited between 0 and 6. So I'm going to keep that in mind. My next step in solving this problem is to find the derivative. V prime is equal to 12x squared minus 108x plus 180. That is my derivative. I need to set the derivative equal to 0 to find the critical points. And notice that since this is a polynomial, the function will never have a value of x where the first derivative is undefined. So I'm going to show you a graph. Here's a graph on my calculator. Okay, not really on my calculator, but on a piece of paper coming from a calculator. This is the derivative function, and notice that it's here at about 2.21. But this is AP Calculus, so I'm going to express this to 3 decimal places. Okay. So this is when x is equal to 2.209, right? That's where the 2.21 came from. And since I'm looking at the graph of the derivative function, notice that this is the derivative function. I'm going to go ahead and use this graph to determine my sign change. So v prime of x is positive, because the graph's above the x-axis, for 0 to x to 2.209. And v prime of x is negative, because the graph's below the x-axis, for 2.209 to x to 6. I have, that's my entire domain. It changed from positive to negative. So the maximum value occurs when x is equal to 2.209. Now I need to go back, and it didn't ask me for the value of x though. It asked me for the dimensions of the box. X is one dimension, that's the height. Height is 2.209. The width is 15 minus 2.209, and the length is 12 minus 2.209. Now, since I don't really have a calculator on me, well, you can pretty much figure out, sorry, this is being multiplied by 2, right? Because it's 2x. Okay. So you can figure out the actual width and height from those expressions. That'll give you the dimensions of the box. So steps are, once again, read the problem, make sure you understand what's going on. We drew a diagram this time because that helped me, and hopefully it helped you understand what was going on in the problem. And the only values I didn't understand were the x values, so I labeled those x values on the graph as the length of the side of each square. I wrote an expression for what I wanted to maximize, and then changed that to a function of x in terms of one value of x. Found the first derivative, took note of the domain, set that derivative equal to 0. So this is when the derivative is equal to 0. This is when v prime of x is equal to 0. Used my graph to go ahead and justify using the first derivative test, and found the maximum volume, found out the value of x where the maximum volume occurs. And this is enough information to go ahead and get those dimensions. This is Monique Morton, Senior Content Director for Mathematics at Advanced Kentucky. Thank you very much.